Alright guys, we are starting a new chapter today. And chapter 3 is on polynomial functions, and our first lesson is just on graphing polynomial functions. So basically what we're going to do is we're just going to be looking at the different characteristics of a polynomial graph or a polynomial function. So let's take a look at that vocab sheet I passed out to you. And these are just the different vocab terms that you're going to see throughout 3-1. And they say match each term in column A to the definition in column B. Do you see how I labeled these 1, 2, 3, 4 and A, B, C, and you can't see D? But I just labeled these. That way we're not drawing lines. I think that seems to be a little easier. Do y'all want to do that? Y'all okay with that? So I'll give you a second to label those before we move on. Alright, so number 1 says the degree of a polynomial. The degree of a polynomial is going to be g. And in the definition it says it is the degree of the greatest degree of any term or any of the terms. And we'll look more at that in some examples in this lesson. But the degree of the polynomial is the greatest degree of any of the terms. In behavior, number 2, in behavior. This describes what happens to the function values as x approaches positive and negative infinity. So it tells you what your y values are doing as x approaches positive infinity and as x approaches negative infinity. All right, leading coefficient is going to be the non-zero term that is multiplied by the greatest power of x, or h. So it's the number in front of the greatest power of x, as long as it's not 0. Number 4, a polynomial function. A polynomial function is a function whose rule is a polynomial. That'd be F. Relative max. Relative max is the point where the function changes from increasing to decreasing. Relative min is going to be the point, it's going to be E, the point where the function changes from decreasing to increasing. Term is the name of each part of the polynomial, so we may have more than one term. We have more than one part of the polynomial function. And then last but not least, your turning point. And that's going to be a point in which the function changes directions. Alright, after you have finished this, I want you to get out your notebook. And we are going to take a look at pages 61, 62, and 63 today. So this says, consider functions of the form f of x is equal to x raised to the n power, where n is going to be a positive integer. Graph f of x is equal to x to the n for n is equal to 1, n is equal to 3, and n is equal to 5. Look at the graphs in quadrant 1. And as the exponent increases, what is happening to our graphs? And what quadrants do these graphs pass through? So let's take a look at these graphs together on Desmos. So they first want us to just look at y is equal to x raised to the first power. And it said look at the graphs in quadrant 1. Remember, quadrant 1 is where my mouse is over here. This is quadrant 2, 3, and 4. Remember, it goes counterclockwise. 1, 2, 3, and 4. So it says look at the graphs in quadrant 1. It's going up, isn't it? Okay. And then it says what quadrants do these graphs pass through? Well, it passes through quadrant 3 and quadrant 1. Let's look at our next graph. We got y is equal to x raised to the third power. So still we're passing through the same quadrants. Would y'all agree? 1 and 3. We still have positive y values as x is getting closer to infinity. But this blue line got a bit steeper than the red line. It's a little bit taller. Or stretched, if you want to use that term. And then x to the fifth. You see how x to the fifth is even taller than that? It's even steeper. But it's still in the same quadrant. So we're going to say as the exponent increases, yep, we just got that email. Somebody wasn't in class when we talked about that. Coach Blocker told me a while ago. So as our exponent increases, the graph gets steeper. And what quadrants were we in? We were in quadrant 1 and quadrant 3. All right. Part B says, now graph f of x is equal to x to the n for 2, 4, and 6. So y is equal to x, and let me take these off. Y is equal to x raised to the second. Y is equal to x raised to the fourth. And y is equal to x raised to the sixth. So here, what two quadrants are these three graphs in? Quadrant 1 and what? 2. And if we started with the purple graph, hold on, it's not letting me do what I want to. All right, if we started with the purple graph, we're in quadrants 1 and 2, but then we looked at the black graph here, and it got a little bit, it stretched, it got a little bit taller, right? Our graph got steeper, and it got even steeper with the red graph, right? So as the exponent increases again, the graph gets steeper. And this time, instead of quadrants 1 and 3, we were in quadrants 1 and 2. C says write two equations in the form of f of x is equal to x raised to the n power with graphs that you predict are in quadrants 1 and 3. So quadrants 1 and 2 first. So let's look at the exponents of our graphs that were in quadrants 1 and 2. What were they? They were all 2, 4, and 6 are all what type of numbers? Even. So if we didn't use 2, 4, 6, will somebody give me an example of one that they think might be in quadrants 1 and 2? X raised to the 8th. F of x is equal to x raised to the 8th. So if we look at quadrants 1 and 3, what's a prediction of a graph that might be in those two quadrants? F of x is equal to x raised to the 7, because we looked at 1, 3, and 5 earlier. All right, you ready to turn to the next page? All right, what is each polynomial in standard form? So standard form means that it has to be largest to smallest exponent. We have to write it with largest to smallest exponent. What is your leading coefficient? What is the degree? And what are the number of terms of each? So we're actually looking at several vocab words here. All right, starting it in standard form. What's my largest exponent I have out of these numbers? X to the fourth. So we're going to start with negative 3x to the fourth power. What would I write next? Minus what? Yep, minus 5x to the third. Do I have anything that's squared? No, so I don't have anything for the squared. Do I have any x that's raised to the first power? 2x, right? So plus 2x. So I've already used the minus 3, or negative 3x minus 4. I've used the negative 5x minus 3. I've used 2x, and that leaves me with plus 6. So that is my equation in standard form. I'm just going to write SF so you kind of know what that is. Y'all okay with that? Next thing they ask us for is our leading coefficient. So I'm going to write LC. Leading coefficient, that was a vocabulary word. That said it is the non-zero term that is multiplied by the greatest power of x. Well, what's our largest power of x here? What's our biggest power of x? That'd be 4, right? Well, what number's in front of x to the 4th? Negative 3. So that's my leading coefficient, negative 3. All right, next it asks us our degree. That's another vocabulary word, I think. Degree of a polynomial says it is the degree of the greatest degree of any term. So it's your largest exponent. What is our largest exponent here? 4. Our leading coefficient is negative 3. Our degree of this polynomial is 4. And then they want us to tell the number of terms. We literally count how many parts to this function I have. I've got 1 part, 2 parts, 3 parts, 4 parts. Okay. Terms was also another vocabulary word, and the definition for that was it is the name of each part of the polynomial. Any questions about where I got any of that? So B, standard form. What's my largest exponent here? 6. So 2x to the 6th plus x to the 5th minus 3x to the 4th plus 4x cubed. I don't have squared, minus 8x, and no constant. So that's our standard form. What is my leading coefficient? What's the first number in front? A 2. My degree is your largest exponent. My largest exponent for this polynomial is 6. And number of terms. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, 5. Use the leading coefficient and the degree of the polynomial function to determine the end behavior of each graph. So leading coefficient, I'm going to write it out, and I'm going to figure out what the degree of my equation is, or of my graph is. All right, so there's this chart on page 136 of your textbook that looks something like this. It says that if the degree is odd, So degree is odd. And if your leading coefficient is positive, okay? Your degree is odd and your leading coefficient is positive. Your graph is going to start down and end up. Well, let's see how true that is. We actually looked at some of those graphs earlier. Our degree was odd. Our coefficient here is our leading coefficient is positive, right? Even if I put a 4 here, I could put a 217 there. See, it's still positive. But do you see how my graph starts down and ends up? So if it's an odd degree and positive, what's going to happen is your graph is going to start down and end up. It is odd and negative. Let's see what happens. Let's just put a negative in front. I'm going to put an equal sign. Which direction does our graph start first? It starts up and ends down. Starts up and ends down. All right, if your degree is even and positive, and we looked at one of those earlier, even and positive, we start up, and which direction does our graph end? Up. What do you think is going to happen if I change this to a negative? Down and down. Oh, I was writing down. I didn't mean to write down. Meant to write negative. So I'm writing all this in the side over here. Starts down and ends down. All right, so we're going to keep that in mind as we answer these next few questions. What is our leading well, first of all, is this in standard form? 6, 5, 4, 3, 2, 1, 0. It looks like it's in standard form, right? So what's my leading coefficient? 2. And degree is 6. So my leading coefficient, is it positive or negative? Positive. And my degree is, well, it's positive, but is it even or odd? Even. So positive and even. So by looking at this chart here, if it's positive and even, I should start up and end up, right? That should be my end behavior. But sometimes what they'll do, guys, is they'll ask you in a way, and I don't want it to confuse you, but they may ask you in a way as, let me figure out, I don't want to word it weird. Let me get my All right, so sometimes what they'll do is they'll say for end behavior, they'll write as x approaches infinity, y or you may see it written as f of x, approaches blank. As x approaches negative infinity, y approaches blank. Well, what does that really mean? Let's think about this. As x is approaching infinity. As x is approaching infinity. So what side of my graph is that? Is that the left side or the right side? Where are my x values getting bigger? On the right. So this is the right side, correct? The right side of my graph. So that means as x approaches negative infinity is going to be the what? Left side of my graph. So let's look at this figure that we drew. Let's look at this figure that we drew. If we're going up and up, do you think it's approaching positive infinity or negative infinity? Positive. So it's approaching positive and positive, right? So that's how sometimes you may see end behavior like that. So I didn't want you guys to get confused if you ever ran across it written like that. Let's try the next one. Leading coefficient, degree, and then we'll write it as x approaches infinity, y approaches blank. As x approaches negative infinity, y approaches blank. All right, what's my leading coefficient of this second part? Not 5. Negative 5. What's my degree? 3. So we've got negative and odd. So let's look at our graph. Negative and odd. Let's look at what we wrote. It'll start up and end down, right? So again, this is still the right side and the left side. So let's look at the right side of our graph. Is it approaching positive or negative infinity? Do it. Negative is correct. Negative infinity. And what's the left side of my graph doing? Is it approaching positive or negative infinity? Positive, because it's going up. What is that? All right, example 3 says consider the polynomial function f of x is equal to x to the 5th plus 18x squared plus 10x plus 1. Make a table of values to identify intervals where the function is increasing and the function is decreasing. So you got a calculator, and this is where I would go to y equals and put the equation in my calculator. So x to the 5th plus 18x squared plus 10x plus 1. And then I want to look at my table. And I'm not sure why, but in both of your equate, or in the example in the textbook and in the example in this book, they started at -3 and stopped at +3. I know there's not very much room to draw a table, so if you want to, you have plenty of room to draw it over here. So we start at -3, -2, -1, 0, 1, 2, and 3. So we start at -110. We've got 21, 8, 1, 30, 125, and 436. It's a make a table to identify, or make a table of values to identify the key features. So going from -112 to +21, am I increasing or decreasing? I'm increasing, so I'm going to write that. But from 21 to 8, what am I doing? Decreasing. What about from 8 to 1? I'm still decreasing. What about from 1 to 30? I'm finally increasing. So, but from 21 to 1, I was decreasing. And from 1 to 436, I would be increasing. Yeah, you see it right here? Maybe that's better. All right, just by looking at this equation, what's our leading coefficient? Our leading coefficient is, what did you say? 1 is right. Our degree is, wait, I think somebody said it, 5. So this is positive leading coefficient, and our degree is odd. So what that tells me is I'm going positive odd. If we go back up to the example 2, tells me that I'm going to start down and end up, right? So this says points where the function values change from increasing to decreasing. So right here, they change, like this point right here, change from increasing to decreasing. Do you see how it's both increasing and decreasing? And also right here at 0, 1, it went from decreasing now to increasing. Those are called your turning points. A point, okay, so then we're going to talk about your relative max and mins in a second. But first, let's draw our graph. We'll go up to and we will go normal, like 1, 2, 3, 4, 5 on both sides, so -2, -4. And then they went up by 5, so this would be 5, 10, 15, 20, 25, 30, 35, 40. And we're just going to plot the points that we can here, guys. So at -2, I've got a positive 21, -1, 8, 0, 1, 1, 30, 2, 1. All right, that's all we can plot. So I know I was increasing from -3 to -2. So I know at this point I'm going to start down because I know I was increasing, right? We said we were decreasing. Well, was that true? Look at what are we doing right here? Are we decreasing? Yep. All right, now what I'm doing is I start increasing again. I know this is ugly, but this is kind of what our graph would look like. Let me see if I can make it look like this. So here's what I changed our settings. Does our graph look similar to that? Yep, it does. All right, rate of change is just slope, y2 minus y1 over x2 minus x1. And it wants us to find the rate of change over the interval 0, 2. So let's think about at 0, I had 0, 1. And at 2, I had 125. Y'all see where I got those points? 0, 1 came from right here. 2, 125, because it told me those intervals, okay? And they want us, so basically, we're figuring out what our slope is from 0 to 2. So, average rate of change equals x1, y1, x2, y2. y2 minus y1 equals x2 minus x1. 125 minus 1 divided by 2 minus 0 is 62. So our average rate of change would be 62 between those intervals. Everybody got this? All right, this one's going to be our last one today. Example 4. That'll be finished. And example 4 says use the information below to sketch a graph of the polynomial function. We've got f of x is positive on the intervals. -2 to -1 and 1 to 2. Let me start by drawing my. It is negative on the intervals from -infinity to 2, -1 to 1, and 2 to 0. So what that means is, because that's back from I think chapter 1, is positive tells me it's going to be above x-axis. Negative tells me it's going to be below my x-axis. It's increasing between negative infinity to negative 1.5, increasing between 0 and 1.5, and then it tells you where it is decreasing at. So you may be like, well, how do I know where to draw? How do I know how to get a graph from this? Well, you start by identifying or estimating your x-intercepts. That's where the function values go from positive to negative. So let's look at where these function values go from positive to negative. We're positive at negative 2 or negative 1, but do you see how it changes right there? So negative 2, negative 1, 1, and 2 are all where it changes from positive to negative. You could have got that from above as well. So that means I have 4 x-intercepts. I've got x-intercepts at I've got x-intercepts at negative 2, 0. I've got x-intercepts at negative 1, 0. I've got x-intercepts at positive 1, 0, and I've got an x-intercept at positive 2, 0. You could get those from these 4 points, or I just looked at these 4 points because obviously you can't do anything at negative or positive infinity. So let's find those. We got 1, 2, put a point there. Negative 1, 0. Positive 1, 0, and positive 2, 0. Step 2 says to identify your turning points. That's your increasing and decreasing intervals. So I've got a turning point at negative 1.5. Do you agree with that? So if I've got a turning point at negative 1.5, I don't really know where because it doesn't tell us accurately, but there's negative 1.5. I got a turning point at 0. Do you see that? Or we can look right here. Negative 1.5. I've got a turning point at 0. I just went down to 3 just because make things a little different. And then I've also got a turning point at positive 1.5, which would be right in here. Let's look at where it says we're increasing. It says we are increasing from negative infinity to a negative 1.5. So that means I am increasing from here to here. I start decreasing at negative 1.5 to 0. So that means I'll start going down. I then start increasing again until I get to positive 1.5. From 0 to 1.5 I increase, and then I start decreasing again at positive 1.5 and down. So we talked about, or your vocab had, relative maximum. Says it is the point where the function changes from increasing to decreasing. We're increasing here, and then we all of a sudden go to decreasing, right? Increasing here, but we all of a sudden go to decreasing. So these 2 points right here are your relative maximums. Relative minimum is a point where the function changes from decreasing to increasing. We only had one of those, and that would be right here. Relative minimum. I'm going to stop right there today, guys, and I want you to do, this should be very easy to do you understand and do you know how. It's not very hard, okay? And we'll go over that tomorrow.